Welcome back to I'm Finally Reading My Brother's Book. I'm Clay Bascom, here with my brother Gavin, theoretical chemist and author of On the Inside of a Marble. In this final episode of Season 1, we're diving deep into the question that started it all. How do we explain the universe? We'll explore the three major frameworks of thought: creational constructions, reductive constructions, and narrative constructions. Then Gavin lays out his biggest idea yet, that the most fundamental principle of the universe might not be matter or energy, but information itself. Maybe the universe isn't just existing, it's computing. It's been an incredible journey this season, full of big questions, mind-bending theories, and a lot of curiosity. But don't worry, we'll be back soon with Season 2, where we'll keep unpacking the universe one chapter at a time. Let's get into the finale. The final episode.
Sinks.
Yeah. Sinks. Entropy.
I thought you were going to do a shout thing.
I didn't know. Yeah. Welcome back, Gavin Bascom. Hey, guess what,
Thanks.
Gavin? I finished your book, bro. I did
That's
it.
wild. I love
I'm
it.
the first one ever.
I love it.
I'm
Well,
pretty
no,
sure.
you're not the first one ever.
Really? They were probably lying to you, bro.
But
Who told you they read your book? Just kidding.
we're going to get that. But I have definitely have had long conversations with people that finished the book. But I'll add to that. I also had a really interesting experience where, like, I finished my own book again after 10 years.
After 10 years.
It was like a pretty cool experience. I'm not gonna, and it put me back in the moment when I first opened the book, when it first got published, and it actually got the physical copy got sent to me, and like how incredibly rewarding that was. I had a similar experience finishing the book this time, because it was like, this holds up. It's still topical. It's still relevant, and we'll get into it, but you just informed me, Clay just informed me before we started, that there are whole conferences of people talking about some of these ideas.
Dozens of people.
That the ideas that they're independent of me and that they've been developing, similarly, and they're
it was really interesting. I got to the point where a big part of the topic of the whole book, and this chapter in particular, is information. And information is a difficult concept sometimes, I think, for people, especially me, in understanding, because it's used in so many different contexts, right? Information, the word, is very different when you're talking about it, when you talk about quantum versus when you're talking about it like in information systems, and you're talking about information you're thinking and stuff. And then we're talking about information, we're talking about computing. And so this was really interesting. So I was trying to Google it, and it was difficult to get a definition specifically for the context that we're talking about. For physics. And when I did find it, it was like, oh, there's a bunch of people saying what Gavin was saying in his book. But they said it 5 years ago. Gavin said it 10 years ago. So, you should hunt them down.
I'm not going to toot my horn too hard, but I will say the sort of the stuff I'm talking about in the last chapter has only become more significantly true than I ever thought possible with the development of computation.
Yeah.
And a lot of that is because that was my field. I'm still my field. I still spend a lot of time thinking about big calculations and how do you do that? But the one thing I would nitpick with what you said, it's hard to get a definition of information. I actually think that's wrong. I think it feels like there are different definitions of information because because language is loosey-goosey and people say things however they want. But
because of semiotic drift.
Yeah, right. But basically, the information is a very simple concept, and it's at the heart of it, it's just representing something. It's just the act of transferring a deduction from one place across space and time. So
yeah, not confusing at all. Super simple. That's what I think of when I think of information.
Maybe not simple, but what I was trying to say is that it is consistent. All of those definitions at some way, shape, or form of, how do I write stuff down? How can I write stuff down? What is the maximum ability to write things down? And how many pencils do I need? And how many papers do I need? It's all those things, how many bits. We'll get into it, but bits are the big part.
Yeah, so this chapter we're going to hit a couple of different things, different ways of thinking about the universe. I think there's a creationist way of thinking about it, a narrative way of thinking about it, and then the multiverse.
No, and it was fun. This was also very rewarding to write because we have all the tools now to finally, and I think a lot of people would read this book and criticize and say, you did it all backwards. You should have started with these philosophical ideas.
Yeah, this chapter could have been the first chapter. That probably would have been.
Chapter 6 could have been the second chapter. But I think what I really wanted to do, and again, I still think it holds up after all this time, is you need to lay the foundation and the groundwork for why these problems are so fiendishly difficult to talk about. It's one thing to just say gravity doesn't play nice with quantum mechanics, and that's been called the catastrophe of the 20th century physics, and then say, okay, and here's what people are working on. They're working on string theory. Like everybody already knows that, but the kind of the point of the book was to make you wrestle with what is actually hard about it long enough. Then you go back and you revisit the obvious stuff, which is like, here's what people have been doing for, 10,000 years, or as long as we've been writing stuff down, people have been doing the first thing, which is the creationist thing.
Love me a good wrestle.
And I also love a good creation myth. Like I think they're beautiful, but we'll get into it, but it is one way to wrestle with the unknown. It's one way to wrestle with the universe and the concept of a universe. And it's kind of the oldest one. The two other ones, like you said, so that's the creational anthropic notion. Then there's reductive anthropic notions. The word anthropic here just means that we're at the center of it, because we can't really get out of that. And that's like, we've been trying to for a long time, but we can't. So the reductive is where we look at that deterministic view. If you keep going smaller, and like, what's smaller than particles? Well, quarks. What's smaller than quarks? Well, nothing really, but we made stuff up and we call them strings sometimes. So you get string theory, and if we think that's how we're going to get a unification theory, and that's how we make sense of all of the cracks in our understanding, then I call that the reductive anthropic notion. And then the last one, which I think is, well, then there's the narrative anthropic construction, which is starting to get a little bit more meaningful. But then the final one is an alternative. There's my favorite is information.
Yeah. So let's get into it. So the first one is creationist anthropic notion. So this is your basic, somebody made it, somebody did it.
Right.
There's some sort of all-powerful being, or doesn't necessarily have to be all-powerful. Not all myths share that. I've always not always, but I've come to the understanding, for me, what makes the most sense of why that's such a predominantly overarching theme throughout history is that's been the major explanation of things we don't know, is somebody that we can't talk to, who's not around anymore, made it. The ancients made it, or there's a spirit that made it. And for me, the reason why that is because, as we're evolving as a human species, one of the first things we did was start making tools. So we were makers, we made things. And then one day somebody looked up from the tool they were making and saw a tree and went, wait, who made the tree? And then you extrapolate that. Somebody must have made the tree. Somebody made the tree. Somebody made the valley. Somebody made the mountain. Somebody made the wind. Somebody made, the rain. Somebody made the earth. Somebody made the sun. And, different myths, different explanations of who that was. Who was that guy or gal? And, I think that's still the predominant way most people still think. I think on this planet, most people think somebody made it all, or something made something, or something made it all with a purpose. And that's fine. That brings a lot of comfort to some people. I would say that the science doesn't support that. I don't think there's much evidence of it, but there's still lots of scientists who do believe that. But like you say in the book, it's unprovable either way, right?
Well, so in the book, what we talk about is, and I'm going to borrow from Dan Dennett here a little bit. I think that the science is complicated. I think that science 100% supports the idea of like intentionality being something that our brains struggle to comprehend. And in fact, part of your brain, there's like two parts of your brain, and there's actually a lot of different parts, but you can divide up your brain in different ways. And there's a dedicated set of features that are just meant to understand what other people are doing, and not just people, also animals, or basically anything that moves around with its own intentionality. Like there's a dedicated part of your brain that's just meant to track that and understand that. And then there's a different part that handles like inanimate objects, which includes plants and stuff,
Mm-hmm.
And so I think like it's very much hardwired into our brains to like see intentionality everywhere, because it's a very hard thing to grasp consciously. And it has played a very important part in how, like you say, how we made tools and how we got control of our tools. But I think the thing which I do agree with is the part that is not testable or falsifiable, or in my mind, even more problematic, is the fact that it's infinitely regressive, which means that any conversation is not productive. Any sort of conversation that has disagreements is this idea that like whenever we can't understand something, or wherever it's like hard to understand a beginning or an end, or we can't, figure out what all means, we say, well, that's because God, there's some sort of creational, and it's not just religion, but also the new brand of it is simulation theory, which there's different flavors of simulation theory. And we'll get into the one that's more from the narrative, but the one that is just like, oh, it's too crazy, man. Everything is so crazy. I can't understand it. There must be some alien somewhere. We must be in some kid alien's jar shaking us around just for kicks and giggles. And like it's like fun, sure, but like for as a serious scientist, you can't take any of that seriously because there's no way to prove it, there's no way to falsify it, there's no way to argue it either. I can't like because you can always just say, well, you don't know. It's like, well, you don't know
Yeah.
either, and you don't know better, you don't know worse.
Yeah.
So
Absolutely. So yeah. So, but I think we both can agree that that's not the one that we think was probably correct.
yeah. Well, and there's another point that I want to mention that you brought up in an earlier episode that I also talk about in the book, which is like when you think about the physics of simulating a reality, there's a thermodynamic principles at play. And the same, which this really comes back to Maxwell's demon that this guy, Chris Krasinski, solved this problem, which is that like information. So in order to simulate a universe, you have to write down a whole lot of information. And so a lot of information has to be kept track of. In order to write information down, there is a certain amount of energy and heat that will be produced or siphoned off from the system in order to write down that piece of information. So information can't exist entirely in vacuum in our brains or on circuits. There's some amount of energy that's required to keep that thing written down or to write it down in the first place, to measure it in the first place. So in order to create a universe, you have to have probably a lot more energy than is in that universe to represent that universe, if that makes sense. So the point I make in the book is that like, yeah, that's true. It'll always be more efficient for whatever malevolent or, not malevolent entities out there to just use the regular reality. Like it's going to be cheaper.
There's actually good physics reasons why we're probably not in a simulation.
Yeah,
but then
absolutely.
again, like you say, the thing that, the people turn to, we're in a simulation. That really is kind of another way of saying like, there's basically a God who created this, and it's basically
but
another
maybe it's
creation.
aliens because God is
Maybe
not
it's
really in vogue
aliens.
anymore. So now it's aliens or some sort of computer program because that's even harder.
But it's essentially the same idea.
Yeah.
And then, but then the next one, this is really interesting. I do want to talk about, what was the next one called?
Reductive anthropic constructions.
Yeah. So, right. So the creationist one is infinitely regressive. The reductionist one and string theory. I never really understood string theory very well. And then you describe it in the book in a way that really finally made sense to me. Kind of what string theory is and, kind of what the reason that string theory exists, like the way they're going about trying to get to a universal theory. So I will probably not be able to explain it very well. So rather than me bumble through it, why don't you explain what string theory is? And why there's so many strings.
Okay, here's how it goes. So if you're trying to understand the physics of a particle, you're trying to make the forces that make the particle move around play nice with gravity. The forces that make the particles move around are discontinuous, which is a weird thing. It means that like atoms don't exist in continuous, nice, smooth lines. They pop in and out of existence all the time. And that's not that we can't see them. It's not that they're going somewhere else. They like literally pop in and out of existence. And people have proven this with experiments many, many times.
Wild.
Yeah. And it's hard to wrap your head around. But so then the math is so powerful that it's easy to do this with math. Easy is not the right word, but it's doable. And you can write down systems that describe things popping in and out of existence by just saying, well, it's just add dimensions. If I add a fourth dimension, and then whenever I'm in the fourth dimension, I'm not visible or not, I can't interact in the 3 dimensions, or if you count time, then the 4th dimension, then we're in the 5th dimension. So if it just pops in and out of the 5th dimension, and we can do that by using imaginary numbers, if you can remember from that chapter. So when you would put imaginary numbers either in the exponent or in the derivative, then you get this ability to write down a nice, neat, continuous equation that has a particle moving what appears to us as being popping in and out of, like a stutter, like a jitter through space. But really, it's moving smoothly through this 5th dimension. And when you project high dimensional structures onto low dimensional structures, that's called a hologram. So that's why they call it the holographic principle. And when mathematicians took this seriously, they found that you couldn't actually do it with 5 dimensions. It's like, oh, well, let's add another dimension. Okay, then it's getting a little better, and it's still not quite working. All right, let's go to a 6th dimension. It's still not quite working. But like, what I will say is that each time you add a dimension, the theories become wildly more complicated. Working with them becomes more complex. Understanding it becomes more complex. Like everything becomes like harder and harder to do anything, and it just becomes like a huge stalemate. String theory got up to 11 dimensions at one point. At least when I wrote the book, I think 11 was the number. I think it was maybe up to 13, and then there was a thing called M theory, which is just sort of being like, we're gonna arbitrarize the number of dimensions, and it might be this, and sometime it'll be something. So it just got like wildly out of hand in terms of the complexity, but it did provide some really interesting mathematics, and some people broke through certain dimensions and ways to write them, which I think will always be valuable. But what it never did was get confirmed by any sort of experiment. And all the experiments went away from it, and it doesn't. So it really kind of went out of fashion, and it doesn't appear to work the correct way, and it doesn't solve the quantum.
Hard physical observational evidence does not support string theory, but the math
No.
is really interesting.
The math is super interesting, and depending on whether you have a chip on your shoulder about funding, like some people will scream and shout about how it shouldn't be taught anymore. But I think like
I was reading one guy's blog recently
Right.
that was very, very upset about the fact
Right.
that people are still giving money, but he's a professor at a college, so
yeah, maybe it needs to be taught at like with a with caveats that this is just math now. It's just fun math instead of like actual physics. But again, I want to go back, and we talked about this in the second chapter, that the assumption is that the deeper you go, the more like unified and holistic and simpler the picture should be, right? That's the assumption with the reductive view, is that if I can just write down the key components, then I should have a way to sort of scaffold up into everything. And the key theory at the bottom should be simple and beautiful. And that went out the window like 30 years ago, because with quantum, well, more like 50 or 100 years ago, because quantum mechanics was like, oh no, it's more complicated. Then we started like, okay, well, maybe if we just keep polishing it, then we'll get there, and we'll get a new branch of mathematics, and that will make it simple. But it just kept getting more complicated. And so adding more dimensions to get a more complicated solution to do what is supposed to be unifying a bunch of other things, but it's actually making them much more complicated to understand. Like there's a lot of physicists who rightly kind of lost their minds, being like, this is dumb, we should stop doing this. Like, why are we still doing this? And people in pursuit of the beautiful theory versus like the practical one. Yeah, anyway, that's the holographic principle, is the idea that we're all living in a hologram of the 10 dimensional strings. Doesn't seem to work though.
Nope, doesn't seem to. Say the scientists, not me. So then the last one, which is probably the correct one, is the what's it called? Narrative anthropic?
Yeah.
Narrative anthropic. So we're back to
Yeah.
narratives.
So this is where the term anthropic principle actually came from. I didn't make that up. This is, I think, harder to understand, but still very beautiful. Like when you are writing down the deterministic view of the universe, and you are equating all of the fundamental forces to, which I still don't fully understand how this works, but there are theories that can sort of map all those fundamental forces onto the early primordial hot soup, and say that like the hot soup of particles gave birth to all these forces in a particular way, which if they were already there, like it's a little hand wavy, it's a little weird, right? And there's some quantum indeterminacies that are important for that. But there are equations, and you can write them down, and you have to tune them backwards. And this is what makes people uncomfortable. You have to start with a very precise Planck's constant, for example. It's a particular number that has a lot of decimals, and I have to start with that number because I know that's true and I've already observed it. And then I have to go backwards and say, okay, I'm going to make the narrative fit this number. So what happened has to produce this exact number. And you do that, and you run the calculation and go, okay, great, this is what happened in the early universe. This is our prediction. But then you start looking at it, but that doesn't actually make sense with any sort of arrow of time or anything. So like, why would that be that way? And there's kind of two things you can do when you start grappling with that problem. You can either say, well, maybe it's not the end or the beginning, right? Maybe I'm wrong about this whole construction of language, which is kind of where I have been going with it. Or you can take the math at face value and say, yes, this must be true, but I can't rule out universes where the numbers were just a little bit different. And, like the soup was a little hotter or a little colder, or the quantum indeterminacies were a little longer, or a little like the inflation was a little slower. And all of that leads to a
Boom, no
different fundamental
planets.
constant with no planets. Or maybe gravity is 2 times stronger, and so nothing ever, you don't expand as much, and like there's all sorts of like differences that would make things, for the most part, not livable, right?
Right.
I think, and people don't understand that when we talk about multiverse. A lot of times, we're not really talking about like Rick and Morty style infinite universes. Right. That's more something that came from the Hugh Everett stuff, which is much more local. Like, how do I understand quantum?
Each, decision, or every atom going in a different direction splits off into a new universe versus, they're being.
So if I bought a red hat, there must be a universe where I bought that other blue hat, and now
Right.
I can like
Yeah.
think of all the crazy hats that somebody could wear.
Yeah.
You know,
It's actually two ways you can get to the, like, it wouldn't be called multiverse, but if you think of, space being infinite, that means technically somewhere else out in the universe, there's another version of you, because atoms have to organize themselves in so many different possibilities. And so there's an infinite numbers of you infinitely far away from you in every direction.
Yeah. Well, and that's an infinity.
Yeah. That's just
thought
an
experiment.
infinity.
Yeah, it's
problem.
an issue with infinity, which is something we have to consider it here. Like it's absolutely part of the story. But yeah, but what I think is like very like the most provocative image that comes out of this thinking, which people are still taking very seriously, and it very much might be the case, is this thing of like a bubble universe, that our universe happened the way it happened here locally from what we can observe. And then outside of it, it might gradually become some other universe.
Right. Bunch of bubbles.
And there's bubbles all kind of floating around inside a bigger...
bunch of marbles in some guy's jar in his desk.
Yeah, right.
Well, yeah, I mean, I have to hark back to our first episode. Or every black hole is its own universe. Baby!
Which from a space-time perspective, that actually makes sense. Like
it could make sense.
Every black hole opens up a new space-time, and so there has to be a horizon, an event horizon with an observational horizon.
Some black holes don't have planets. They're a bunch of goo. Some black holes make planets like ours. And you get life, baby. Get people wondering about where are we.
Another way to think about it was like a lot of these ending and beginning theories of the universe, which we all sort of agree that the Big Bang is a thing. It's not that we agree. We can see it and we can measure it and we can listen to it. So the Big Bang is real. We know that happened. But what is in debate still, and I heard Brian Cox say this in an interview recently, it makes me really happy, he was like, well, the word beginning might not actually be correct.
Sure.
And like,
there could
it's
be
just
something before the Big Bang.
Hottest.
The hottest.
And it's the hottest / oldest that we can
It's the only
observe.
thing it's the oldest thing we can see. Therefore, we don't know.
The beginning.
I mean, we think of space as being infinite, right? So why not time?
Yes, right. In fact, it probably should be infinite, but that's
probably should be.
Yeah.
So if you think like there was no beginning of the universe, it's just always existed.
There's that, and then there's also just, I mean, I have a different interpretation. I think that they're both valid at this point because it's hard to test. But the other interpretation is that beginning is a malformed question,
right?
And there is no such thing as a beginning. There's only hottest. And like oldest becomes hottest at some point, and like you're never gonna get past that. That's kind of my pet theory. Yeah, but the bubble universe is a cool thing. And then for people that are this far along, hopefully you finish the book with us, because I really loved this idea that I had where we end the book on this note. Well, we're skipping the information part. We'll go back to it. Where it's like, I think that we're inside of a time bubble, and that's the bubble. Like it's like the universe is sort of progressing itself through time at a rate that's different than we can observe. And so there are these time walls, but they're horizons more than anything. It's like we talked about horizons in chapter 2 and 3, where things appear in a certain way at a distance, and they're very much real, but only observed from the faraway vantage point, right? And in the same way in relativity, the fact that I can observe somebody with a different time, like if and I will observe it differently than that person, or the parallax is different depending on how fast I'm going. We have to take the physical reality of what horizons are, both temporal horizons and spatial horizons, as a physical reality that we can measure, because we're measuring it right now every time we look out. And the only way that works, in my view, is if the universe is something much more complex than like a big glass marble.
I think we can agree on that. I think we can agree it's not a marble per se.
It is a bunch of information.
There you go. Circle it back. Way to drop in there.
It's a bunch of inferences. Like it's a bunch of.
So for me, time years ago, I heard an explanation, because time's one of those things that doesn't have to exist, right? It is a dimension, but there's different theories that talk about how like you don't actually need time, or time it doesn't really exist in certain, if you think about it in certain ways. And the way that always made sense to me was, if you have a system that has high entropy, meaning it's completely disordered, time becomes meaningless, right? Because there's really nothing changing in a way that you could create a narrative, right, that makes sense. Whereas if you take something with very high entropy and then you introduce, like I would always do coffee, and then you pour milk in, suddenly as the milk has a very low entropy, it's all still together and there's ordered. and the, coffee and the milk are separated. And as the milk slowly, bounces around, the molecules bounce around and dissipate into it, becomes, entropy gets higher and higher and higher until it becomes, the highs it can get in that system. And in between the two, so as soon as the low entropy is introduced until it gets back to high entropy, you have time. Where you can explain, these particles are separated and they're bouncing around, and you can come up with a narrative time. Like you can track all the different ones. But once you get to the point of really high entropy, time becomes meaningless. I saw someone explain it that way years ago, and that clicked with me, and I was like, okay, yeah, I could see how in certain circumstances time no longer matters. Still doesn't really help me understand this special theory of relativity where time is different for different people. You get close to a black hole and suddenly you're going faster.
Well, I think there's two things there. So it's the arrow of time is the thing that you're talking about. So when you go look at particles from a close-up lens view, and only a close-up temporal view as well. So I'm only watching it for a short amount of time, and I can only see very far away from that particle. There's a thing called the law of microscopic reversibility, which is that if you observe something that wouldn't be exactly equal in the reverse time direction, then you've broken physics. Like, physics is symmetric, always, no matter what, with reference to the time. And the only place that you can say, no, look, time was moving forward based on observation is in a complex system like that, is when you move out enough and there's an emergent phenomenon. The way that Einstein measured time, which is very much still valid, is just the clock. Like, he was literally not, there's no, and people don't understand this. This is a hard thing to understand. He didn't invent a new way of measuring time to do special relativity. He literally just said, no, if you are holding a clock and I'm looking at your clock and you're moving away, then when the second hand is moving around, by the time it gets around, because you're further away, it will take a little longer for the second hand to reach the same time around. That's what he was actually talking about. Is like, it will look like your clock is moving slower if you're going towards me and faster if you're, and like, that's literally what he said.
Wild.
It's not magic about like time speeds up and slows down. It's just, it just looks like it speeds up and slows down. And if you take that like real for real, if you take that literally, you get special relativity, and it solves a whole bunch of problems with other things that you observe. And that sort of inability to distinguish between the way things look when something's moving, we also have to apply that to things that are far away. That has to be real. The way it looks has to be real in some sense. And we also have to think about time. How do you zoom out in time, and how do you zoom in time? So if you zoom in time, you have to add frames, and the thing you're zooming in towards might run out of frames in its own time frame. And that's my pet theory of that's what's happening with quantum mechanics. We've zoomed in so far that the energy that gives rise to those particles is running out of frames. So when you just start to see it going pop, 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 because we're putting frames in where there's no frames anymore because the energies just don't exist. We're putting them and we're going, this doesn't make any sense. This is really weird. But in the same sense that like clocks look like they're further away when they're moving away, like you're looking at something really far away in time and energy, and it looks like suddenly it looks like a one of those zoetrope things. Like, but
that's cool.
You know what I mean? Like,
hey, the zoetrope brought it back. Zoetrope.
And it's the same when you go back and try to do cosmology, except now we're taking frames out. If you take a whole lot of frames out, i.e. look backwards in time, then there is a fundamental disconnect. An even better way to put it is like when you measure gravity. Gravity is a macroscopic object phenomenon. It's
correct.
It's negligible at small scales. To the degree that so when you zoom in really close and particles are now popping in and out of existence and you're having this like discontinuous everything, you have to treat space as a discontinuous item where there's Planck units. Whereas when you zoom back out, space is smooth.
Right.
And because of the Planck units, it gets so infinitesimally small that space is smooth now. When space is smooth, you can do things like warp space-time, and that gives you gravity. You can't warp space-time if it's discontinuous.
Right. This is almost like if you zoom in on a picture to the point where you're just looking at a bunch of pixels.
Yes, right.
Yeah.
And that is, again, this makes sense if you're thinking about it from an information perspective.
Mm-hmm.
But where physicists have lost their minds for the last 200 years is thinking about it from a fundamental perspective. It's not an information problem anymore. It's a fundamental problem. Like, no, but the particles have to actually be popping in and out of existence. They can't just look like they are. They have to actually be because I measured it. And it's like, well, it's not that it's the measurement is how they look. Like that's the sort of hallmark of the modern theory where we're going to go. And then I think information theory will take us.
Yeah. The guys that I was researching today basically were saying that they think that there's a good chance that information is basically the most fundamental aspect of reality, meaning pretty much everything comes out of information, which I have hard time wrapping my brain around. But basically, like for the longest time, we've always assumed, what I can see is the most fundamental, right? And that's particles. It's light particles, not light, but like it's specifically, particles. It's matter. It's the things that we can look at, and like we can measure it, we can do that kind of stuff. And we assumed that was the most fundamental, aspects of the universe. It was matter. And what these guys are proposing is that no, actually it's information. And then they started saying this phrase that was interesting, is that basically our universe is a computation.
Yes.
I thought you'd like that.
Yes,
yeah.
100%. I 100% agree with that.
I thought you would. But so basically the universe is a computation. And then the one guy did break it down. I understand a little bit about computers and that I understand that there's bits and there's zeros and ones, and that, you have these patterns of zeros and ones that you put them together and you can come up with a computer program. And it's pretty phenomenal just off of 2 bits that you can basically encode massive amounts of information with just single bits. And he was talking about how you can take something like the English alphabet and you break it down to its component bits, and it's like 16 bits or something, I forget the exact number. Using those bits, you can have the English language. I think that's such a small number of bits that you need in order to have something as complex as like language. And how you basically think of every particle, like every matter, every particle in the universe has some bit of information tied to it. And in the past, we've always thought of as, the most fundamental thing is the particle itself. The information was just hitching a ride. It was just there.
Right.
Whereas probably a more accurate way to think about it is actually, no, the information is the important part. The particle is hitching a ride.
Yeah. It's hard to make your brain think that way, right?
But so now I have a new catchphrase, which is, the universe is a computation, baby.
The universe is a computation. I think, these are very speculative theories, but they're very fun to think about. There's a part that I talk about in the book that we should cover that I think was what really finally spelled it out for me and what sold me, because I remember reading about a bunch of different disparate pieces and finally sort of put it together as I was writing the book, which is, there's a thing called Shannon entropy. And Shannon entropy is
Shannon.
Claude Shannon, very, very smart mathematician, who basically when you go to encode something, we all have this idea that zeros and ones are easy to come by, right? Because I can write a 0, I can write a 1. But if what you're trying to do is transfer a signal across a wire, you can't, you could say, you could do dashes and dots, right? Like Morse code, that's your zeros and ones. But what if there's already noise on the line that is the same speed as your dashes or your dots, right? So then whenever you go to...
This messes up your Morse code.
You can't do it. So then the Shannon entropy is to say, given the amount of noise in the line, what is the amount of it? What's the minimal encoding scheme that I need in order to be able to transfer messages with fidelity across the line? So now, to actually understand entropy from this perspective, you have to understand something about the base noise in the system. And it becomes like a relative thing. And without getting into the details, there's like all of these crazy cool things when you apply the concept of Shannon entropy. It solves a bunch of fundamental problems in cool ways. But one of them is that with quantum computing, there was a conundrum that came up that everybody started to not understand how this could possibly be true. With quantum computing, you could entangle particles and you could send them across the galaxy and then do a computation. And that computation could start on one side of the galaxy and instantaneously complete at another side of the galaxy. And so then people should be able to break the speed of light law.
Right.
So not that
sending messages.
Because they're sending messages, right? What Shannon entropy says is that in order to make a message start at point A and go to point B, you have to encode something. You have to have a way of saying, no, but A means this and B means that. So spin up means this, down means that. And like the way quantum works is you can't assign any of those things before you send the particle. So the noise, which is the noise part, that's part of the noise, is that there's some are going to start there, some, which means that like the Shannon entropy limit is that you still can't, even though you can do computation faster than the speed of light, you can complete calculations faster than the speed of light across multiple distance domains, but you cannot communicate the specific result that you got across that time, across that distance, any faster than the speed of light. That will always be the fundamental limitation.
The speed of light, man, it's
not a physical limitation. It's an information limitation.
Right.
The information cannot be transferred unless it goes into some sort of bit that has been predetermined across a physical time. So like there is a very interesting point there that there's a universal maximum to something that is not a physical thing at all.
Yeah. So the reason the speed of light is such a hard limit is because of information.
It's a theory. It's what finally made it click, but it's what made it click for me that if we're going to get an outside of the box view of the fundamentalness of our universe, the stuff we've been wanting so bad for 200 years with unification theories, it's not going to come from strings and it's not going to come from quantum gravity. It's going to come from information theory. Like, because it's the first time that somebody, and people are just sitting on it, they didn't even realize, but it's like, there's this huge insight into how it's like, okay, light solves an optimization problem. And there's a thing called Snell's law, and it's very complicated. It's not that complicated, but it's complicated enough that I won't go into the details here. But when light refracts off a surface and goes to point B, when going from point A to point B through different mediums, it automatically chooses the fastest way to get there. And it doesn't know beforehand, because from the perspective of the photon, it is instantaneous. So, but the fact that it gets there the fastest possible, it's always the fastest, and that is always the way to solve the problem of where the light path is going to go. It's always going to go the fastest from point A to point B. That's solving an optimization problem, and nature is solving an optimization problem. And like, it doesn't ever do that. Nothing ever, that doesn't exist in nature. There's no fundamental optimization solving problems. The same way that we talk about anthropic, like fact that our universe has a Planck's constant that it has is not an optimized feature,
right,
is the one that makes us think, well, why this one and not all the other ones? And why? And that's why it's all anthropic, because, well, we exist in this one because we're in this one, right? Well, yeah, that has to be the answer. That's it. You're never going to get better, more satisfying answer than that. What we want is an optimization question, because we are clearly the optimal of something,
Just ask my wife.
Sister. Yeah. So anyway, I'm getting a little, I'm not in the weeds, but I think
hysterical.
The point that I'm
just kidding.
I hope that you see the point that I'm driving at here, which is that the information being able to optimize things, that there being like inherent information optimization in information theory, was super exciting to realize, because it brings a fresh perspective to physics. And anytime that a field has been toiling under the same assumption for 200 years and not produced anything, maybe not 200 is harsh, but, for a long time and not produced anything.
I would say physics has it's produced something in the last 200 years.
It has. And we've learned a lot about black holes. I'm not trying to denigrate, and we've learned a lot about, but if you go out and you read all the stuff that they're doing, all the state of the art on black holes, it's all about information. It's about how much information can I encode on the surface of a black hole. Like, all the physicists that are out there doing the circuit, like, they are super excited to talk about how the amount of information that can be inscribed on the surface of a black hole solves problems in quantum encoding.
Crazy.
Try to make sense of why that would be true. Because there's a much deeper thing that we're missing. It feels like we're right on the cusp of getting some really satisfying click about why our universe is so hard to understand and behaves in all the weird ways. We have all these clues, but we just haven't been able to like sort of put it all together yet. And
well, yeah, another guy I was reading was talking about how, in biology, DNA is essentially like the information, right? It's like the code that sort of builds out that, and then there's a similar vein in chemistry, and then why not in physics? The information is the building block of everything.
Yeah, which I guess maybe the DNA thing is probably one of the better analogies, because to put it in the language that we've used in the podcast, that we developed in the podcast, in order to look at something very far away, i.e. like bootstrap a measurement across a long time scale, you have to do something really tricky. So you have to write down information, and that information has to come back at different intervals at different rates, because of, remember the whole taking out frame thing.
Mhm.
Like anything that is trying to continuously measure something that long won't be able to do it for practical reasons, or because this timescales don't line up. So if you are trying to design an organism that is going to last a long time in the Earth conditions, you have to design a system that will like sort of spontaneously read from disk and then change features. And there's really, really fascinating science done by guys at well, I'm thinking of a particular guy at MIT, but like where they can show that the timescales that evolution plays in, it looks a lot like an AI like system self-optimizing, but at these like 100-year
Yeah.
timescales.
Yeah, right. Which is
It's like fine tuned, and you can like look at the DNA, the history of the DNA formation, and you can show that like it's genetically modifying itself in the way that AI algorithms like
so
rewrite code.
I actually had an idea for like a I don't know, like a sci-fi novel or something, which is like, you know, I don't know, some sort of super being or AI or something that it doesn't age is trying to like tweak life and genetics. And the way that they do it is they would like set up parameters to be like, okay, I think I'm going to make the evolutionary natural selection push in this direction, and then they'd get in a spaceship, go around a black hole, and come back 10,000 years later because they basically speed up time. Like, okay, cool. Come back and be like, oh, made this weird creature.
Yeah,
But you know, that would be fun. The problem with that idea of like, well, what if we did that? Because originally the idea was like, oh, well, I'll take a spaceship and shoot it out into space that has like, you know, the natural selection pressures on the spaceship, and when it comes back, I will have like created life that can live on Titan or something like that, like a human being. Problem is the way physics work, you can't actually do it that direction. Like, you know, you can go and basically slingshot yourself into the future. You can't slingshot something else into the future and then come back to you, right? So you could never practically use it. Then I thought, okay, well, what if you lived on a planet near a black hole? Then you could send the spaceship out to the slower time and then come back to you. So
that's a great premise for,
yeah, right? That'd be kind of cool.
What is it? Who is the guy? What's the Adrian Tchaikovsky that wrote the
Yeah,
some stuff like that?
Yeah, well, he's got some good stuff. So anyway, yeah, no, this is fun stuff. So I'm excited to now know that information is the most fundamental myth of the universe.
I think so.
It's all about the bits, baby.
But it's less. I don't know. Yeah,
you don't like the phrasing.
It's so hard to, because I feel like there's really something really, really cool here. Like it's just so hard to put it in words. But
you got to write a song that's called "The Universe is a Computation."
Yeah, that sounds catchy. No, I guess the last analogy that I made in the book, which was fun, I just like throw one more thought experiment at you in the last like 2 pages, like you haven't done enough yet, you know, at this point. But which is like if you've seen videos, I think I saw a YouTube video of this like as I was finishing the book, I was like, oh yeah, I just throw this one last little thing in here, which is if you can drop a dry ice bomb underwater. So if you watch bombs going off underwater, they're really funky because there's this interplay between the rapid expansion and then the water pushes back and then expands and then it goes down and then it gets hot again. Like as it goes back down, as the volume collapses again, then the pressure expands and then it goes back even further. So you get this like sort of jagged, like boom, 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 boom out, which is not unlike what happens to our early universe, because we've measured like some slowdown and speed up, which is totally wild, right? But then the thought experiment that I did instinctively, which should sound familiar now, is go inside of that. Okay, say you were living inside of that and you were far away from those horizons and you didn't know anything about the water or the dry ice. All you knew, because you're an ant and you're living in a very fast timescale compared to the timescale of the expansion. So now if you write down all the universe laws in terms of eternal absolute immutables, which would mean the ground doesn't move, right? That's an eternal absolute immutable. The ground has always stayed in one spot. It will always be in one spot. Colors are red. This color is red. This thing is, charge repels like charge and it attracts not like charge. If you write down that version of the universe, you will get really confused when that dry ice bomb goes from expansion to contraction. You go, what the hell just happened?
Like I get confused when the Big
Everything
Bang
is
does
backwards.
that.
Everything is backwards now because suddenly everything was going this way and suddenly it's going that way. And the pressure was. So now but instead, if you wrote everything down in terms of information, what that would mean, it would actually look a lot like our early deterministic view of the universe, which is where we had to say, okay, I don't know about charge. I don't know about the floor being steady, but I know that when I measured it back in 1982, it was here and it was going this fast. And I write that down. And then I just measure it every couple of years for forever. And then you can look at the trends, which is information. That's what information is. Things in relative to each other. It's the fact that I took a measurement at some point and I wrote it down. And that measurement and all of the measurements adding up, you wouldn't be so surprised. You say, well, it was speeding up and then it slowed down again. And then it started speeding up. And then but we can't do that with fundamental particles because we're so fixated on this view, this reductive view, that our universe is made up of the particles. When if you go and talk to physicists that work on these particles, they don't talk about, it's not like the proton did this. There is a little bit of that, but it's more like this, especially when they break down past a proton, it's like there's a 392 electron volt signature, and then there's a 291 electron volt signature, and which is all just energies. It's all just energy. Everything just becomes energy, and it's not really like a specific thing anymore. It's just this, So to me, we're already doing it to the degree that we can, which is that everything should be information. But I guess the whole point of the book is that it shouldn't be so surprising and it shouldn't be so magical that the particles bounce around when you start thinking about it this way, right?
More like a jump scare for me.
Sure.
Cool.
Anyway, that's I don't know if you made it this far.
Yeah, man, that's cool. I did enjoy the dry ice bomb thing. That's an interesting. I've never actually seen that. I should look that up. That sounds cool. But I did like the analogy or the parallel with the early Big Bang. But it's something interesting that I think it's a good thing to point out with the Big Bang. That's just kind of just another stretching your brain moment, is to realize that the Big Bang happened 13.8 billion years ago, and we can see that. And so you would think then, okay, so if you look at one side of the universe or one side of or one edge of the universe and then look at the other edge of the universe, and this should be, what is that, 26 something billion years ago? No, it's 93 million years in between the two. That's how much expansion that we've had inside of our loaf of raisin bread. Yeah. And so, which is hard to wrap your head around. You're like, wait, so we can look back into the past 13.8 billion years ago. But then if you were on one side of our universe and then started to, travel, it would take you 93 million light years to get to the other side.
Billion,
93 billion
you said
years?
13.8 billion. And then
93 billion years to get to the end. Yeah, which is
bigger.
Wild. Which is wild.
Because of the expansion, which is also was hard to figure out.
Yeah. Which is like, wait, what? What's making it expand? Dark energy. What's dark energy? You don't know. Nobody knows. It's a placeholder. It's going to turn out to be something.
I think there's a lot of people saying it's going to turn out to be information.
Information!
It's it's the amount of information the universe is keeping track of itself, which is.
Well, the universe keeping track. Why? Why isn't an accountant? Why is the universe an accountant?
Because when we say universe, we're not actually talking about a thing that is independent of us observing it, right?
Yeah. We're inside the wave function.
Yeah, right. Okay,
beating a dead horse over here.
I know, but it's just think of it this way: if you can't observe it in, just a good word for it, but in a reference frame that would give you 90-degree angles, right? If the cube, remember from the beginning chapter, when you look at it in the way, you can't actually see the right angle version of it, which is the invariant. That's the word I was looking for, the invariant version of it. When we say the universe is keeping track of itself, we're not saying that it is a big accountant. We're saying that in order to look at it, you must go through this distorted version of it, where information distorts your view and space looks like it's expanding, and and then that distorted version of the event of the horizon effects that make everything look different. And you can only see the book kept version of the universe, which is one where there's 67% energy unaccounted for, because that's the amount of stretch and pull that the observation has to have, because you're cutting frames and stuff.
Cool. I'll have to go back and listen to that. I'll listen to my own podcast to understand it.
I mean, this is some of my favorite stuff in the whole world. So if anybody
Talk
anybody
about
listens to
meta.
that and understood what I meant and want to talk about it, please reach out. Let's talk about it some more.
Yeah. No, that is funny. I of our 2 listeners, we have a few listeners, but
That's not true.
I do ask people who listen to the podcast, so do you have any questions? Like, no.
Nope.
It's just like,
no comments, no
I
questions.
have questions. Mostly, what?
Well, what I learned when I was today years old was that there is a conference of people talking about this. So I'm going to go to that conference.
I don't know. I think it sounded like it might have been kind of exclusive.
Well, I'm going to email.
Yeah, I guess
Clubs are not that exclusive. The clubs in this
physics.
world are not that exclusive. You just email them
just
all
be
and
like,
say,
hey, I want to talk about this. They're like, really? You talk about it?
Okay, were you willing to pay for your own plane ticket? Yeah, go.
Like, sweet. Well, I want to go.
Let's do it.
Get out of town.
We'll figure out which the next one, and we'll do it. We'll go together and
get out of town.
Shout every time. Whenever you don't know what's going on, just stand up and be like, but information.
I need more information.
But what about information?
Feel like, wow, yeah. And then now we have AI just generating information. Is that going to destroy the universe?
No. It's not how that works. Yeah. AI is like 100% how we're going to say this the right way. I don't think AI is going to solve this problem for us in the way that it's solving like coding.
Yeah, because AI is dumb.
Or image.
It's just
I'm not saying it's dumb. It's very, 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 very
model.
smart. It's very, very smart. But I think that people that study, and there are very smart people that study the optimal way to encode information into these large models. And there's people that study the optimal way to retrieve information from these large models. And it's not straightforward at all. And then the models always follow this very funky path that nobody talks about, which is that they get trained on a specific task, and everybody always goes, just give it a bunch of examples of like the right solution and a bunch of examples of the wrong solution. And then it like kind of doesn't kind of work. It kind of works, but it kind of doesn't work. And then they go, oh, I don't know, give it a bunch of examples of people working on it and then the right solution. And there's some version of that where you give it like people doing it and finding the answer, and then it can like get the right answer. And then people come after the fact and use more simple architecture, but they have to like really finagle the architecture of the training. Like the trainings get really overcomplicated to do it correctly. Then people come in and they use a much simpler architecture to train on the results of that model. And so there's this like funky thing where like humans are like the ants that went and like did all the little hard piecework and they figured out one solution, another solution, but you can't see the whole thing. Then the first model is like, we'll give it enough of the ants too. And it like kind of carves out like a little bit more of a river through the solution. And then the big guns come in and say, okay, there's an easy way to do it. But you can't just take the big gun and put it on the ants the first time. It doesn't work.
Emergent properties, man. Emergent properties.
And so every time one of those paths is carved out, we learn a little bit more about how information works.
Cool.
Yeah.
So it sounds like we don't need a particle collider that encompasses the solar system. Just need better AI.
Yeah, good callback. I don't think we need better AI.
Well, we're going to get it because AI is getting better
absolutely.
all the time.
It's getting funded.
Whether
but
you want it or not.
Yeah, no. And I use it every day. I'm a big...
Yeah, I use it a lot.
I'm happy about it. But my point is, I think the fundamental nature of information is going to become clear. And then we're going to be able to, as humans, make conjectures and test them about what's going on with the universe. But I think that we are living inside it's not a big simulation. It's inside a big inference.
Computation.
An inference. An inference is a very specific ML term. Like when you have your model, the model has all the information in it. You have to query the model. So you have to say, now give me, if I give you this input, give me this output. The act of going from the input to the output, that's the inference. And I think our universal measurement is necessarily constrained to a big physics inference.
And speed of light.
If you get away from well, if you get away from the reductive view that like there's these fundamental eternal laws that govern everything, and that's not it at all. There's just one really big complicated narrative that we can't see. We can only see part of that big complicated narrative. The narrative itself is constrained because the narrative is information. So the narrative is constrained in this way that the information has been, you can only see the part where the information has been written down in some way, which means like, because here's another thing to wrap your head around. It's hard. If an atom bumps into an atom and changes its perspective, it changes its direction. If I knew it was going in this direction earlier and then it got hit and it went another direction, that's information.
Mm-hmm.
I didn't have to write down where the other atom was. It's just as long as I know that it changed its direction, I know something happened, and that's information. So, like, there's a lot of information that's being generated all the time by atoms bumping into each other.
Too much information.
But in order to measure that information and write it down, you'd have to have the right initial conditions and then the right observations. And it's a complicated process. It's impossible in a global sense. It's very much possible in local senses. But then to infer at greater ones, there's going to be a big chunk missing from the inference because you don't have the initial conditions correctly. You're only guessing at what they are. Anyway, and that gets back to our anthropic thing. We're stuck inside the measurement. We're always going to be stuck inside the measurement. So it's always going to look weird to be looking backwards and imbuing all this stuff with the features that it needs, because you don't know what you don't know, and you can't see what you can't see.
Mm-hmm. Because dark matter
Actually is not that mysterious. We know where it probably is. Dark energy is the one that's mysterious.
Yeah. Cool. Well, this has been great. So I'm going to stick with my new catchphrase: the universe is a computation. Thanks. You heard it here first. Or maybe not. You probably have heard it somewhere else first. All right. Till next time. And that's a wrap on episode 8 and on season 1 of I'm finally reading my brother's book. I did it. I finally read it. From relativity to dark matter to the idea that the universe itself might be a computation, this season's been one wild ride through space, time, and information. Thank you for listening and exploring with us. We'll be back soon with season 2 and even bigger questions about reality. Until then, stay curious.